Speed measures how quickly an object's distance changes. The standard measurement of speed is meters per second. To determine the speed of an object, the distance traveled and the time it took to cover that distance needs to be known. The formula to calculate this is v equals d divided by t. D is the distance, t is the amount of time, and v is the speed, but known as velocity. Instantaneous is the object's speed at a given moment. Average speed can be calculated by the amount of an object traveled over the given time. Acceleration is the time rate of change of velocity. Acceleration can mean three things: speed is changing, direction is changing, or both at the same time. Acceleration does not have to be speeding up, it can also mean slowing down. When acceleration is slowing down, it is negative. When acceleration is speeding up, it is positive. An object can change acceleration by the same amount of velocity each second. This is called constant acceleration. On a graph, it shows a straight line.
First, the ramp was screwed together and set up on an angle 10 holes up. Next, two photo gates were placed onto the ramp. One was located 10 centimeters down, with the other at 20 centimeters. Then, the car was placed on the opposite side of the ramp, with a wooden piece of the car sticking out of the side, which would run through the photo gates. Before rolling the car down the ramp, using a lab quest, it was connected to photo gates A and B. Next, the car was rolled down the ramp at multiple distances and speeds were recorded. The car was rolled down 8 times, and each time moving photo gate B 10 centimeters down, and leaving photo gate A at the original spot of 10 centimeters after every trial. Before every new roll, the lab quest was reset to 0 for accurate results. After every roll down the ramp, the distance from photo gate A to B was recorded. This process was used for the investigation of position versus time. To investigate the acceleration, the angle of the ramp had stayed the same. Photogate A was placed about 30 centimeters from the top, and photogate B was placed another 20 centimeters down. The acceleration of the car was calculated by dividing the change of speed by the change in time. The acceleration was observed after 3 trials, moving the photo gates into different positions at 20 centimeters apart. After every trial, the acceleration was recorded using the formula speed at B minus the speed at A over the time from A to B.
In this lab, the car's position was investigated as well as constant speed, increasing or decreasing speed. During Figure 1, speed increased each time the distance changed. The object remains constant at 1,000 from point 627. The object was not constant for the whole time because speed increased. In Figure 1, the object has a positive acceleration because the speed is increasing. The graph shows an increase in distance as the time is increased. Speed at B increases and decreases as time goes on. Acceleration also increases during this. There is no uniform motion. Trial 1 shows that speed at A and B is slower than Trial 2 speed at A and B. But, however, the acceleration is greater at Trial 1 than it is at Trial 2. One source of error could be having photogate B at 90 centimeters. This could affect your data by not recording the actual time for photogate A. Another source of error could be having photogate A plugged into section B and photogate B plugged in section A. This could affect your data by having the wrong data for each photo gate. The independent variable was the car. The dependent variable was the photo gates, and the control variables were the distance of each photo gate and the height of the ramp.